So alright, so now let's talk about how we calculate the change of shear force, internal shear force and the internal bending moment. What I want to say is this. For example, let's consider a beam segment, a beam problem. So I have beam here, okay? And then let's consider, let's say the beam is subjected to some, let's say the internal forces, the external forces like this, and then also the concentrated load and bending moment or whatever, blah blah. And then we want to consider a small segment here, small beam segment. And then if you look at this beam segment, there must be the internal shear force here, and then V here. And then also on the right hand side, there must be change of internal shear force, isn't it right? By what? By delta V, okay? Some change. We need to calculate this change. And also, if you look at the left hand side, there must be the reference bending moment. And then if you measure the same bending moment in some distance, what I mean in the right hand side, there must be also change in the bending moment too by delta M. So we want to calculate this quantity, okay? So we want to calculate this quantity, delta M and delta V, okay? That's why the title of the lecture note is delta V and delta M, okay? Alright, so now first subject is I want to consider a small segment measured by its length is dx, okay, dx. And then we want to consider the segment is subjected to the distributed load Q. Its magnitude was measured Q. The unit of Q is what? The force per distance, okay, force per distance. For example, so 1 kilonewton per meters, okay? That is the unit of this distributed load. Distributed load in 우리말 분포 하중, isn't it right? So let's say, let's check the change of shear force for the distributed load condition. So that's what we want to say. So as I told you, according to our definition, if you look at the point X here, point X, there must be one reference the bending moment and then one shear force, isn't it? So if you look at the situation, the same internal forces, so in dx distance, there must be change in the shear force and the change in bending moment. So we want to calculate the change of shear force and the change of bending moment. So at first, I want to consider force equilibrium in the vertical direction. For VERT is abbreviation of vertical direction. Sum of all the forces in the vertical direction should be equal to 0. So according to this, let's count all the forces. Okay, so we have one force upward. So that's it. By the way, I forgot to introduce the coordinate system here. So let's introduce the coordinate system for the calculation of the force equilibrium. Okay. So let's choose upward direction is positive. Then if you do that, okay, so we have positive force here, positive force and the positive force, isn't it right? And then if you look at this guy, it's downward, so which means minus, so minus symbol. That's why we have V and dV, isn't it? And also this is downward. But this is the unit of Q is force per distance. That's why to check the force equilibrium, so we need to multiply the length where the force, the distributed force Q is applied. That's why we multiply Q dx here. You understand? So here the V is cancelled because their signs are opposites. So only what is remaining is, if I do one by one, and then the remaining is these two are remaining, isn't it? That's why, sorry, not this guy. These two are remaining. So, minus Q dx is equal to dV, isn't it? So let's divide the x both sides by dx, then we obtain this equation. So if you integrate, if you move dx to the right hand side of this equation, and then if you integrate both sides, then we obtain, let's say this is point A, This is point A and point B. If you do that, then any change in internal shear force can be calculated by the integration of the minus sign of integration of distributed the force Q, the integration. Is it clear, right? Simply speaking, the change of internal shear force between these 2 points, nothing but just integration of the minus of distributed load in that distance from A and B. And then, easily speaking, this is nothing but just area of distributed load Q. This is more intuitive way to understand this equation. Okay, change of internal shear force between 2 points. 2 points is nothing but just area of distributed load with the minus sign. Okay, isn't it, right? So now the next step. Now let's talk about how we calculate the change of bending moment. So next object is here. We just calculate the change of shear force between these 2 points if this beam segment is subjected to distributed load Q. Okay. So now let's talk about the calculation of bending moment here. So again, to calculate the bending moment, the equation that we have to check is equilibrium condition. The sum of all the moments should be equal to 0. So let's count the moment. So again, to check moment equilibrium, so we need to introduce a coordinate system here. The coordinate system for the calculation of moment. So we want to consider this is positive, counterclockwise. So let's check this guy because it is opposite sign, so minus m, isn't it, right? Minus m. And how about this guy? M plus dm. That follows that direction. This is positive. Okay? And then let's choose for the calculation of moment. We need a reference point. Let's choose this is our reference point. So the contribution of this shear force to the reference point is equal to 0. That's why we don't have to consider this shear force. The V times the arm length is equal to 0. Now how about this guy? So we have non-zero arm length, isn't it, right? But it produces the clockwise moment. That's why V plus dV, and then this is the distance dx. That's why we have minus sign. Is it clear, right? And how about let's look at this guy. And then the force is what? The Q is force per distance. That's why to change it to the force, it becomes Q dx. And then the distance for the calculation of moment is what? Half of dx, assuming the distribution of qx is uniform in this dx. Okay? And then make sure that we want to consider dx is pretty small. So if you consider dx is very small, then small times small is what? Very small, yeah? So that's why we want to neglect this. And then we want to neglect this. And then also, because of sign, these two are cancelled. And then finally, what? Finally, we have one more term. The change of shear force, that's the small change for the distributed load. And the change, and the dx is also small. Because small times small is also that this is cancelled. So if you rearrange this equation, the derivative of bending moment in x direction is given by the shear force. Okay, this is final equation. So let's move dx to the right hand side of this equation. If you do that, change of bending moment between these two points is given by the integration of the shear force distribution. So make sure the shear force is function of x coordinate. Also, we can understand this equation intuitively. The change of bending moment between 2 points is given by the integration of shear force. But this is nothing but just area of distribution of shear force. Okay, so we have very similar closeness to between these two equations. The change of shear force is given by the minus area of distributed load. The change of bending moment is area of the shear force diagram. Okay. So now let's check the case with a concentrated load. So up to now, so we consider the change of shear force, change of bending moment caused by the distributed load here. So now in this part, we want to consider the change of the shear force and change of bending moment with a concentrated load. So, but this is very simple. The concentrated load is nothing but a limiting case of asymptote of distributed load. So if you consider dx is infinitely small, then integration of q dx, okay? This is the concentrated load P. Is it clear, right? So if you consider this, let's go back to this equation. So let's consider limiting case. This is just the P, okay? Just the P. The change of shear force is given by the minus sign of concentrated load here. This is very simple, yeah? So if you have load, then my V1 change is minus P. That's it. It's very simple. And then how about the change of bending moment? Is there a change of bending moment? Because now this, as I told you, this is the limiting case. In limiting case, dx is equal to 0. The arm length for the calculation of bending moment is equal to 0. That's why there is no change in the bending moment caused by the concentrated load. Next one is change of bending moment. Change of bending moment, the internal shear force by the concentrated moment. So let's say we want to consider concentrated moment. Why we want to consider a counterclockwise concentrated moment? Because we, in the case of external load, we want to use this coordinate system, and then also we want to follow the right-hand rule. Okay, that's why we want to consider default positive according to external the coordinate system for the consideration of external loads here. So now again, similar to the previous discussions, we want to consider reference moment and reference shear force. And then if you consider some distance here, and then there must be change of shear force and change of bending moment. Okay, because this is a moment, if you check the force equilibrium in the vertical direction, there must be, we can easily understand that there must be no change in the internal shear force. But by the concentrated moment, to satisfy the moment equilibrium, if you check the moment equilibrium in this direction, we can easily understand that M1 to satisfy the moment equilibrium is minus sign of applied external moment. Okay, so bending moment changes abruptly at the point of external moment. Okay, this is the point. And then by the concentrated load and the shear force does change in the vertical direction. Okay, so we have analogies in these two conditions. So here we calculated the change of shear force and change of bending moment in beam segments caused by the external loads. So we considered distributed load, we considered concentrated load, and then also the moment here. Okay, this is nothing but just the integration. So we can understand change of shear force due to the distributed load is nothing but the minus sign of the area of distributed load. And then change of bending moment is also the area of distribution of shear force. Okay, here let me stop this video here. In the next video, so we will discuss how we construct the shear force diagram. What I mean, distribution of shear force and distribution of bending moment. Okay, let me stop my video at this point.